Hello, everyone. My name is Manuel Flores. I am a professor in the Juarez University of Durango State. I am located in the laboratory for scientific calculations in the Faculty of Chemistry Science in the city of Durango, Mexico. And I am here to present you this poster that will be presented in the C1 symposium of the Congress of the Materials Research Society in Mexico that is being held in Cancun this 2022. And this poster is going to be in the Symposium of Emerging Materials for Clean Energy and Environmental Remediation Applications. The title of the poster is Titanium Dioxide Nanoclusters. Well, this is a single nanocluster co-sensitized with two anthocyanidins using DFT and TD-DFT. So this is a theoretical work using the program Gaussian version 16. For the sake of time, I will be going through the poster, focusing on the images to explain as fast as we can and as better as we can the content. So this is a co-sensitization process that we are trying to do in a 5-unit cluster, as shown here in figure 5. We see that this nanocluster has 5 titaniums, which contain the 2 oxygens by each titanium and form this cluster, this arrangement. So we will take a couple or 2 different pigments to do or to achieve a co-sensitization process on this semiconductor. This nanocluster is a semiconducting of dioxide. Actually, titanium dioxide is known as the best photocatalyst. And the function of the organic molecules that we're trying to use here is to sensitize this semiconductor so it can be more effective when used in the dye-sensitized solar cells or any process that has wants to activate the charge transfer on this kind of device. So we used anthocyanidins to as dyes, as natural dyes, to do the sensitization on this semiconductor. So this is cyanidin, the one in letter A is known as cyanidin. And the second molecule that we used is malvidin. We see in this table 1, a list of the more common anthocyanidins and some of the details or the features that form the structure. See that these cyanidin and malvidin have some differences. Mainly, they work on different parts of the electromagnetic spectrum. For example, cyanidin is associated with the orange and red colors, while malvidin is blue-red color. You see in the R1, R2, which is located here in the general structure of the anthocyanidins, they also contain different molecules. Here you can see the malvidin has the methyl group. Here is the OH in the case of the cyanidin. The cyanidin is a more simple molecule because it has more features that make it, let's say, less complex than malvidin. For example, here we can see that the rings, the 3 rings are in the same plane, while in the malvidin, we can see that there is a torsion angle here, located here. So the third ring here in the left it forms almost a 90-degree angle with the rest of the molecule. So these differences in geometry become very important when we try to combine or to interact these molecules with the semiconducting oxide. To understand a little bit the effects of these differences, we can see first of all that the configuration of the molecule, well, is different. We can see it clearly in the chemical formula for molybdenum and cyanidin. We can see that they have the same number of carbons, but they have different number of hydrogens and different number of oxygens. And then if we see the image here, we perceive, even though this is a 2D figure, but we can perceive that in a three-dimensional view, these molecules are very different. So when we take them and we combine them, we can obtain something like this. And well, why do we want to do that? Well, we see that individually the molecules behave electronically in certain way. We see them to have a better visualization of that. We produced this figure 6 where the molecular orbitals are shown for each individual without any interaction, only themselves. Each one of the participants in these systems. For example, here is cyanidin alone by itself, molybdenum alone by itself, and here we show three different titanium dioxide nanoclusters. We will use in particular for this work the third one, which is the 5-unit titanium dioxide nanocluster. But on purpose, I left these two to visualize that they have different behavior, even though they all are titanium dioxide, but the structural differences between the nanoclusters and the number of units that they form, leave us with different configuration of molecular orbitals. This is a very known property of the materials, but we measure it using these computational tools. So we see that the energy states here before reaching this we consider the LUMO, which means the lowest, is the highest occupied molecular orbital, is the HOMO. And the LUMO is over here in top. The energy states on the let's say pink color, some strong pink or violet color. I don't know if I interpreted well the colors, and in green is the home. Well, these are organized different for each one of the species that will participate in this system. So the combination of them will give us something that we expect that will work better on sunlight and will produce a better charge transfer mainly, but for sure we know that will behave differently. So we put together this system by placing in the center the 5-unit titanium dioxide, and in the sides first we created a system which contains 2 cyanidins. So we have cyanidin on the left, cyanidin on the right, and then we removed one of the cyanidins. In particular, I can say that we removed the one in the right and replaced it by molybdenum. Then we compared what happened in the molecular orbitals. and also in the absorption spectra. We calculated the excited states to obtain this absorption spectra. We can see that there is a very big difference here. We are still not totally satisfied with these results. We know that the difference is there. But you can see here in the purple color a very small peak, which corresponds to the combination of cyanidin and malvidin. This spectra is very small, and it is very extended, but very low. The peak is very low. The oscillator strength is very low. So in the case of cyanidin interaction with the titanium dioxide, we see this is a very strong peak here around 500 nanometers. So it's a very interesting result, but we still want to improve our theoretical method that we're using. Actually, I can say that this result that you are seeing here is have been very challenging. So we have a lot to do with this theoretical method to obtain better results and visualize better what is going on here. At this point, we see that it's very clear that the interaction between the different molecular orbitals of the species participating in this system. For example, the molecular orbitals for the cyanidin combination with the titanium dioxide is here in the first let's say energy states that are shown here. Then in the second graph here that is next to we can see the cyanidin malvidin combined with a titanium dioxide. So there is a difference in the effects of the molecular orbitals, which at this point we think that we can continue improving these results and producing more data. So I hope that you liked this topic, this poster, and if you want more information or more data, I will be happy to share with you. Remember, my name is Manuel Flores, and I am located at the Juárez University of Durango State. Nice to meet you. Bye-bye.